Yeah, so this is kind of continuing on like a couple sessions with time series itself. Um, we should be getting into the project right now. I know everyone's kind of doing a little catch up, so that's perfectly fine. This should some of the stuff's review. So I know like Eric, you might not have seen this. Ala, I know we kind of went through this part before. Basically, know that these notebooks are there online, so you can check them out and everything like that. Levy, if you're welcome to check that out too. I can send you the link afterwards to make sure you access this. But big part basically is making sure, like for visualizing our actual time series, making sure we can do those different, what's it called? Showing our different distributions. I remember like one you can basically get into is like your histogram. So these are like the common stuff, your density plots, right? So these are more like distribution of data itself, not so much of temporal based plotting. So like a time series, as we talked about, is like very temporal focused. So that's when we start getting some really interesting stuff. So some of this stuff can also be done with a box plot. And I think I had an example here, is that you can kind of see, like, you can see the distribution amongst different times. This is one way to kind of help you visualize parts. And then one of my favorites is actually using like a heat map, for example, to actually, see if I can get this one. Yeah. So sometimes heat maps, I think, can be really particularly useful to plot out like a whole bunch of information. Otherwise, you're plotting all these lines together. You can get a general feel for like the trend if it's really obvious, but a lot of times, you're losing the exact details. So sometimes, like, I think a heat map sometimes does a good job of making that good balance, okay? So just that was kind of quick review stuff. Our different trends, right? Remember, like, really trying to do is try to get to the stationary trend. We're trying to get to the point where it's stationary so we can actually see that difference. What's it called? Like, we can see, like, I call it the noise, but really it's more like the residuals of the actual time series. So just remember that that's the part, like, your kind of goal to get to. So they can say, hey, if I can get down to basically the stationary trend, then I can actually pull out information from this and, actually do some interesting things. So remember our different types of trends. We have like our stationary, which basically, I think I talked about this before, is that we're trying to basically get to this part was like just the noise or just the residuals, basically the stuff that you can't necessarily explain with the material you have already. That's one that's really interesting. Okay. Otherwise, we have things like the linear trend. Like, this one's pretty simple. Like if you see it going up or down, we'll see some basic models of how that looks like. Exponential is very common. Basically, exponential tends to happen when you have things getting multiplied on top of each other over and over and over again. And I think I mentioned this before. Kind of fun thing about exponential trends is that at the very beginning, they tend to look very linear. And then as they go further, they actually go off into this extra direction. So something to kind of look out for, especially if you're doing modeling. A lot of times there'll be these points where people will model it to be a linear trend and then they undershoot it because it's an exponential trend instead. So kind of fun stuff. And then periodic, which we'll see a lot of, times, because a lot of times there's different, sequences and like businesses and stuff like that of like where you see like, this pattern going over and over and over again. And that kind of leads us into like doing like differencing. What else we have? Trying to list off a whole bunch. So we can do things like our differencing. We can subtract the rolling mean, which can be useful. For example, you're trying to see what overall is happening. So like this right here is an exponential trend. And so I can actually calculate that rolling mean, which is essentially that window of like past points. And that's what that red line represents, is saying, okay, here's like the average of those past few points. And we can actually take that and subtract off that average that's moving forward. And this might hopefully make sense of like why we would actually subtract the rolling mean. And it's because, like, if you think about it, if you start off really high at a value, let's say the stock market, if you start off your value very high at the beginning of the month, it's more likely the next day that you'll also have a higher value, or at least, around that value. So if the thing's going up and up, you kind of want to subtract that off so you can see, well, what's the little patterns within there? And that's where if you subtract off this rolling mean, we can actually get this part. And that's closer to like what we're doing with differencing. It's not quite exactly the same, but basically if we're differencing, we're essentially shifting it over and say, okay, what's the difference between those different, time periods? So you can see here, I think this one's that's actually come from the curriculum. I think there's also one with New York Stock Exchange. Okay, I'm not going to go over that because I don't have an example to go. But you can see here, for example, the temperature over 365 days, well, over 1981 to 1991. You can see there's a pattern here. And by differencing it by basically that period of 365, and note that that period is just based on the actual, what's it called? The actual data point. So if it's collected every day, there's gonna be 365 days. So you would expect this pattern to repeat 365 days. And this is where we basically do a difference between the 365 days. And basically you can start seeing more of a noise thing. You're getting less of that pattern that you would kind of, that periodicity, okay? And that kind of leads us into like decomposition. So again, these are all kind of quick overview. I know like Ally, you've like seen this probably now like a couple times, but like, you know, it's hopefully a good refresh too. So we get into decomposition, right? Basically our decomposition is like we're trying to tear apart this time series and break into its components, right? And so I think this is the one that we kind of talked last time, kind of just walked through a little bit. This is, again, I think this is pretty much directly from the curriculum. So I kind of gave you guys something that was familiar. And so you can see here, for example, we have a trend going through the number of passengers. And we can see it's going up and up and up and up and up. So we can see, okay, there's clearly a linear trend going up here. You know, maybe it's debatable as exponential, but it looks pretty linear to me. But one big part you can see here is that it's going up and up and up, like each, what's it called? Each like fluctuation is getting larger and larger and larger. So that should immediately put in this like, oh, okay, like that heteroscedasticity, you know, if there's this heteroscedasticity there, we need to basically change that out. So one thing we can do is a log transform, and we can actually see it still stays pretty linear, and we actually get most of that heteroscedasticity in there. And then once we have that, it's like, okay, cool, like that's pretty good. Let's go do decomposition. Basically, we're trying to break it down into its trend. So like the linear part, the seasonal part, basically, you know, the seasonality of its periodicity going back and forth. And then hopefully that all we're left is the residuals. And the residual we're hoping is actually stationary, okay? And so we can do this basically like, you know, this is through stats model. So I won't walk through this whole part. And again, this is through the curriculum. And basically we're just plotting each individual part, the trend, the seasonality, the residual, and then the original log transformation. So we have the original log transformation here. We have the linear trend that pulled that part out. It pulled out the seasonality, and you can see it's pretty much the same all the way across. And then we have this right here, which was our basically our residuals. And this one we can actually, from this point, say, well, is it actually stationary? We can do a Dickey-Fuller test, which is kind of like a hypothesis test for saying, hey, is this trend actually stationary? And we can actually do this, and we can say, hey, there's a pretty high chance, if we go through here, its p-value is very, very small, so it's a pretty good chance that it is in fact stationary. Or we can confidently say it is stationary. One thing to kind of note, like I think Aubrey, who was joining us last time, kind of mentioned, is that the residuals are the interesting part. Like, you know, like you can talk about like why is there seasonality or why is there a linear trend? Like those are important parts too. But these are the residuals are kind of like the really interesting part because there's stuff that you haven't like really considered yet. And so she mentioned, for example, there's like this lower, like, you know, like fluctuation, like in this time period and stuff like that. It's like, well, why might that exist? Like, well, maybe that's possible, like during the Cold War or something. Maybe there's something between 1954 and 1958. Maybe there's a reason like people weren't really traveling as much. This is where you can start seeing patterns in there. And what's interesting too is you can see in this residual, we still almost look like at the very beginning here to have some kind of fluctuation. And that kind of fluctuation more or less kind of goes away. So it might be interesting in the future to kind of like look at, say like, okay, do we actually have, did we break apart this this trend as much as we could, or is there other things that we can look into? All right, so that's kind of like the basics of like all we did for the past, you know, 1 or 2 sections, right? Anything that you guys want to add on, or questions, or kind of like, wait, I don't remember that. Ooh. Okay, I know Eric, this was kind of like, that was a huge like crash course, like there's so much more we just passed over too, but no, that's kind of the basics of like what we're looking at time series. All right. So this kind of leads us into some modeling. So like Olivia has talked about, like, you know, you can actually get into the part of the modeling for the project. You know, once you basically do some visualization, doing some processing, you want to actually do some modeling and say, hey, can I predict off of this, right? And that's, I think that's where, like you said, like it can be a lot of fun because I think modeling is one of those things you're like, ooh, I'm predicting the future, or I'm predicting off of this. And that's when we'll get into, actually after this project, we'll go into more like other machine learning methods like recommendation systems. Well, actually, I don't know if we have recommendation systems next, but we do a bunch of other machine learning aspects and stuff. And I think that's when it's like, oh, cool, we get to do some predictions. So it's all coming together, right? So I'm gonna go ahead and close this part. So this is all new to you, Ala. So I don't think it's something we've seen yet. So this is good news to everyone. Well, maybe not new to you, Ala, but at least it's, you know, new seeing it from this angle. So basically, we're starting with like some basic models. And so the curriculum kind of talks about a couple of them, for example, the white noise model and the random walk model. And those two will actually lead into some more advanced models. For example, ARMA and SARMA. Basically, those ones can be used to do more prediction. But first, we're going to start with very simple. So the white noise model in the curriculum, they kind of did this link to this article. Pretty good one to go through and stuff like that to see another way of going through this model. But basically, this white noise model, as you might guess, white noise means pretty much random. Do you guys actually know that? Like, I realize that not everyone necessarily knows white noise literally just means randomness. Like, when you see like your TV screen go to white noise, it's actually basically doing all the random parts. Kind of fun fact is because it uses all the frequency, like you know that static from white noise, like you can hear it and it's very piercing. It turns out you might think like, oh, it's only mostly the high frequencies. This is completely off base, but it kind of gives you an idea of what white noise is. But it's like supposed to be all the different frequencies, so completely random. The thing is, it sounds very piercing, very high pitch, and the reason why is because humans are very good at detecting high pitch noise. So it turns out there's other things you can do. For example, one thing you can have is pink noise, and basically what it is, it readjusts the sound to be more random. And so it's more, even though it's not random, it's perceived as more random by the ear because we're more sensitive to high-pitched noises. If you ever get a chance, just search on Google, like on YouTube, pink noise, and not like a band or anything, like pink noise, and you'll find something that does like static, and you'll hear it, and you'll notice that like what I've noticed, I'll do it to like concentrate, it'll block out a lot of sound. So it'll like make everything blend in. It feels like muffled, in my opinion. So anyway, white noise. It's basically just randomness. So basically, we're going to take something that's random and just say, all right, put some random noise into it. Okay. So the few properties that we have a fixed constant mean. Okay. We have a fixed constant variance, and we have no correlation over time, also called like autocorrelation, right? So the pattern is random. There isn't like a preference between one over the other part. Okay. Note that like if we say a Gaussian white noise, basically we're talking about a mean of 0 and a variance of 1, because that's like the classic Gaussian, okay, our bell curve, right? All right, so I'm just going to the example to actually code it up, right? So what I'm gonna do here, I'm gonna basically run this part and basically just create some data starting from, January 1st, 2015, and just do 100 days. Okay. And then what I'm gonna do underneath here is say, okay, I'm gonna create some random data. Average temperature, we're gonna say that's the mean is 10, the standard deviation of 3, and we'll just randomly generate this from NumPy. Okay, so I make sure I actually run this. Otherwise we'll not get an error, or we'll get an error. And this will actually be my time series. So this is kind of like, okay, I'm just starting off with this random data. And you can see here when I run this now, we can see that it's more or less random. And I could run this again, and you can see I get new random data. Ooh, right? So there's hopefully like you'll probably see patterns in here, and this is why, because people are very good at finding patterns even when they don't necessarily exist. But trust me, it is in fact random, at least normally distributed or random. Okay, so this is our very basic model. Like you're just like, all right, let me create some white noise. Any idea why we might actually care about creating white noise to begin with? Like, I don't know about you guys, like this sounds kind of useless to me when I first hear about it.
Maybe it's something to compare something else against.
Yeah, good. So one's good comparison, right? If you have a bunch of randomness, you can say, okay, what does this look like? Another part is a little more subtle. Has anyone got an idea of why else we might use random noise or white noise? And I'll give you kind of a hint is how would this deal with like putting it with other models? Okay, so one thing to kind of notice is that we'll never get like perfectly predicted, because in reality, there's too many factors of either measurement or just not knowing what are the right variables to measure. And this is kind of like, you probably know this intuitively. If you see a perfectly straight line, you don't expect that to be natural. You kind of tend to be like, oh, that must be generated in that sense. For example, if you see a perfect circle, no one drew that. It was a computer-based thing. So when a person actually like draws, and I'll just draw a little for my point, it's like when you have a straight line versus like someone drawing it, even on the computer here, you have these kind of wiggles. Okay, that's kind of what we're doing with white noise. You can actually insert this into other models and say, okay, well, I expect to be some kind of noise in there. I don't expect it to be perfect. And this can help you basically build a model that's like, well, I have a little bit of white noise. And this can actually be a huge factor of saying, if I cause a little white noise, does this model actually take off in a certain direction and stuff like that? And you just might have just random stuff that's going on. Okay, so white noise, even though it seems very basic, it's actually like a great like building block to start from. Okay, so any questions on that? Okay.
Yeah, just
yeah.
How does inserting false data into your model help with your prediction?
I know it sounds really counterintuitive, right? You're like, shouldn't we predict as best as we can? The best example I can kind of do this, like for example, if you're generating data, and this is, to be quite honest, time series is not my strong expertise, but I do know, for example, white noise data can be really good for data augmentation, and they're also good for models. The way you can kind of imagine this is that, like, if I said, all right, computer, generate this data that's going to be perfectly along this curve, right? What the computer is going to do is just going to make dots in this perfect curve. And we know that real data doesn't actually form like this. So in a lot of ways, you're overfitting onto this part. You're saying, oh, make this too perfect. And so by adding a little random noise, essentially, you get a more realistic set of this data where instead of going across here, you have something that looks kind of like this. Like maybe you have some points that aren't quite right, but it's more realistic and you can actually model off that. If your model essentially is trying to be too exact, where it's like it thinks it knows all those parts, you can actually, in a sense, like fit your model and say, okay, like I think this is going to happen. And this is where, depending on like the situation too, for example, to be honest, I'm getting a little probably too deep here, but one part is like chaos theory. It's like one chaos theory is like, well, if you have these small fluctuations and you never expect those small fluctuations ever to happen, some systems really emphasize those points, and you can basically thinking like, oh, this model will perfectly go this way every single time. And then it turns out like, oh no, it turns out by this system, a small fluctuation can make a huge change. And you would have never seen that without applying basically random noise. And random noise basically just means there are things that you don't know, you can't measure, or you haven't done a good job enough to measure. So like the weather system, for example, it's like, there's no way for us to ever perfectly model that exactly. So you might add a randomness in there to make sure you account for that part that you can't measure. Is that kind of answer?
To a certain extent, I guess it's when you're worried about overfitting, making your information less exact. So generating random information that's around your data points, but not along the same line. So therefore, your model automatically needs to take into account other information.
Right. Yeah. It's like, this is especially true for like if you're doing data generation, or if you're trying to go over and over with the same model, you wouldn't want the same exact process every single time. So if you're testing, you want to put in a seed, so you make sure that randomness, like for example, I put like a random seed of 13 just to basically say, okay, so produce the same thing over and over again, so I don't get any weird results. But in reality, it's like, okay, you actually want some randomness because you know the real data that you're going to read into is not going to be, consistent every single time. So hopefully that kind of makes some sense. Okay. Again, like what we're trying to do here is trying to model the real world. So in a lot of ways, by adding this real worldness of random noise, it can help basically your model versus like completely keeping it out. Okay. Cool. All right, but good question. All right. So going into like our next basic model is our random walk. So it's kind of like upping our game from like our just our white noise model. So one thing here, again, there's another article that's pointed from the curriculum. This one is kind of an interesting, is that our previous value is going to influence the current value. So our white noise model didn't care about what the previous value is. It's essentially just a bunch of white noise along the average. And you can kind of see, hopefully from this data, well, this outlier kind of messes it up, but it should be about an average of like 13 or about 10. Oh, I guess that is about right. So you can see that the average is 10. And basically all it's doing, if you imagine this as a scatter plot, it's just putting a bunch of dots randomly. It doesn't care about, what time it is and stuff like this. Where a random walk, we actually care about where we started from, right? So this is like, if you are, at like, $100 a share, on day, 5, the next day, you're probably going to be give or take around $100 a share. You're probably not going to suddenly drop to like $5 a share or $500 a share, like, just fluctuating every time. You kind of expect this to be somewhat correlated from the past, right? But of course, there's some little difference in there, right? And so just know that there's a strong dependence over time. So we actually have this formula here. And, the formulas are always like really useful. Like I say, like, if you're not a very like mathematical person, it might be kind of intimidating, but they're kind of like, in my opinion, kind of like poetry. They're kind of like condensed forms of like what's going on here. So this y basically is our actual series, and this t is like what time it is, right? So basically it's saying that y of t, so the next time that's coming in, or whatever time you're looking at for that data point, it's dependent on whatever it was last time. So t minus 1 means like yesterday or last month or last year, however that frequency we're putting it into. And then plus is epsilon t. And this epsilon t is white noise, basically just a little bit of randomness. So this is, again, like, the reason why we put this randomness in there is because you wouldn't expect it to be exactly the same every single time or increase by exactly the same amount. You would have a little bit of fluctuation in there. So note that this is a white noise with mean of 0. So the reason why we'll have mean of 0 is we're actually going to have a variation of this, a random walk with a drift. But basically just means that it's going to fluctuate. It's going to have a chance of going up or down, from the point that it was previously. So if you imagine, like, if I had a little, let me see if I can draw it real quick. If I have my graph right here, and I have my different point, right? I have my first point right here, okay, and this is time. Okay, so this is our t point, our point t, and then our next point is t1, or t minus, or sorry, I'll say this is t minus 1 since we're doing that. So this is t minus 1, and this is t. So to figure out, like, where does t go, like, what is this point going to be? It's like, well, it's going to take this value here, and then it's going to add on this random value that's going to be, on average, 0. But sometimes it'll be a little above, sometimes it'll be a little low. So let's say if you flip the coin, or you have your random number generator from your binomial distribution, and you say, okay, it's going to be right here. Okay, and then you take this point right here and say, okay, what's the next point? It would be t plus 1. Well, to get to t plus 1, you would look at the previous point and say, okay, is it going to go up or down? And you say, oh, all right, you do your random number generator and says, oh, it's going to be down by this much, and it goes down right here. So on average, what would you expect like this line to look like? So if we didn't have, well, let me ask you guys, if we didn't have this white noise, what would our graph look like? Like if I drew like some kind of line. I think I saw Eric do it. That's a straight line, right? Yeah. So it just basically lets yt equals t minus 1. So you start off at this point, and basically it would just be point. So this is kind of going back to like why you use white noise. Like, well, that's not good enough, right? Like that's not, like, it's just not going to do anything. So what instead we do is like, okay, what's going to happen instead is we're going to have something that's going to be around this point, but it's going to kind of fluctuate around here, right? It's like sometimes it's going to be small, sometimes it's going to be big. And what's interesting though is that I kind of did more of a white noise, which is actually wrong. What you'll see instead is like, okay, like you start here, sometimes you go up, and then you might go down, and then you go up, down, up, down, up, down. So you'll see some parts, for example, go up and up and up just because the flip of the coin, it's getting, many increases, and then it'll have one decrease. But on average, it'll basically stay on the part. So what you'll see sometimes in these kind of models is you'll see it kind of like fluctuate up, and you're like, oh, it's going up. And then all of a sudden, they have a bunch of down spurts, or they have a very large down spurt. But on average, over a long period of time, you'd actually expect it to be whatever it started off at. Okay, so let's see what this looks like in code. Any questions on that? Does that make sense to everyone? Okay. So I think it makes more sense when you actually do it in code. So if I run this code now, okay, I'm going to generate 1,500 points, so a little more than I had before, starting from January 1st. And this right here, basically, I think this is directly, let's see here. Some of this is from the curriculum, some of it's a little different. So I try to change it up a little bit. So we're going to generate basically starting at y equals 0, or this is the initial point, our y0 is 0. And we're just going to say, all right, these are our original values. We're going to create our time series right here with our values from here. Okay. And I feel like, oh, is this right? It seems wrong. Okay. That's right. This is our, okay, this is what I was saying before. This is without a random noise. So I was like, why is this going on here? So we don't have anything interesting, like nothing happens. It's just basically a flat line, right? So every date basically has just a value 0. Now what happens, we can do the same thing. So we can actually add our average, what's it called? Our white noise in here. And so the curriculum does this really smart thing with the cumulative sum. And basically what's happening here is that we're going to generate some random noise, this epsilon, just like we did here. You can see it similarly. We created some random noise. So we're creating our random noise right here. And we're saying our standard deviation of 10. So we have a high variance. Our average is 0. Okay. and this is going to be our epsilon. So this is going to generate basically a long string of, or not a long string, but it's going to take endpoints, which is 1,500 in this case because we ran it up there. And this is going to basically make 1,500 random points, that are averaged on 0. Okay, and so just to kind of prove it to you guys a little bit, if I run this right here, I go ahead and insert epsilon, and then let's do the mean. You can see here, it's a little higher than 0, right? But you can see here it's about 0. If I do like standard deviation, we can see it's about 10. So just to try and show you like those are the different points. But if I do, for example, like the max, right? It's probably gonna be somewhere around 20. Oh, it's probably about 35, right? And then our minimum is gonna be somewhere in the negatives, right? -35. So it fluctuates all over the place, okay? So now I can take this epsilon, which is a bunch of random numbers, right? And basically it's each date has a random number assigned. And what I can do then is say, well, what's gonna happen is I'm just gonna add up these random parts, because the reason why is that this equation, if I start with 0, and I'm trying to kind of walk this through, it's like, why are we doing a cumulative sum? One, because it's efficient, but like the reason why we can do that is because it's smart. So we have our y0 is equal to our, well, we'll just start off with 0, right? And then our y equals 1, or y1 is equal to this guy, 0 plus, I'll just put like epsilon 1, right? And then our y2 is going to be equal to, y1, which is just, we'll just kick out the 0, epsilon 1 plus epsilon 2. And a great writing right now. Those t's and epsilons look probably the same. But the point is that you can start saying, oh, I'm just adding up the, what's it called? The little noise. And you say y3 now. Well, y3 is just this stuff, y2. So if I just put this part together, epsilon 1 plus epsilon 2. It's really hard to write with the mouse. Plus epsilon 3. Okay. And so you can see here, you can see the pattern now. It's like, oh, I'm just adding up all the different errors. So instead of having to go through a loop, going through and say, okay, get the last one, previous one, add this up, go through that. You could technically do that, but we're not cavemen, right? We can do better than that. So this is where like we can actually use, smartness, like, oh, like, hey, we're just adding up all the errors. So we're just doing a cumulative sum, which tends to be much quicker in NumPy than trying to do a full for loop. So now we have all these randomness, we put it through, and our data that was started off this way ends up being this cool, really fun, fuzzy stuff. And so you can kind of see is that what we'd expect is that over a long period of time, it would be about 0. And you can see here, there's some stretches of very positive parts, and then all of a sudden we have some very negative parts. And so you'd expect this, just like if you flip a coin, you don't expect to flip a coin and get heads and tails and heads and tails and heads and tails, even though it's 50-50, you expect some heads and then some tails, some heads and some tails. But since it's cumulative each time, you'll actually see these trends kind of come upwards, okay? And hopefully this is starting to look a little more realistic compared to just random noise. So we're starting to see a little bit of a pattern in here. So this is where we get into a variation from random walk. But before I go into that, does everyone understand like how this graph basically was generated? Thumbs up, sounds good. Any questions or comments? No? Okay. So now we can start doing some funny stuff, right? It's this random walk with a drift. So the only difference in this equation is that we add a single letter, or a single number every single time, right? And so back on when I was writing the y0 equals 0, y1 equals epsilon 1, y2 equals epsilon 1 plus epsilon 2, that still exists. But every time we do that part, we're going to also add in some value. In this case, I'm going to use 0.5. And so what would happen in that case is that we're going to have that same model, but we're going to have a new increase, or it could be a decrease too. It could be a negative number. But we'd have that same value on each part. So what would you guys expect this graph to look like in compared to our original random walk? Anyone got a guess? Okay, so I see, can you explain that a little bit more?
It's going to trend more upward because you're basically compensating for drops by adding in more positive value.
Yeah, I think that's a good way to think of it. You're kind of like compensating for like, sometimes it's going to go up and down, like there's going to be this randomness, but we're going to increase, in this case, a positive number. We're going to keep adding that point. So you can imagine like when I do the y0, y1, y2, your C would basically be like plus C, plus 2 times C, plus 3 times C, plus 4 times C. So you'll have it increase every single time. Okay, and so in this case, it's a positive number, so we'll actually see an increase. So we'll see something similar where we see now, this is the original, the blue right here, and this is the same exact data, but in this case, I'm just adding that C. So I didn't redo epsilon, I just kept epsilon the same. And you can see here, C is just being added every single time. So we actually get this increase in this orange right here, going up and up and up. If I put this negative, as you might guess, it would tend to trend downward. So this is, again, like a random walk with a drift. The drift is C. Obviously, if this value is too large, so for example, I put like, let's say 2. If it's too large, that drift is going to be larger than the actual randomness going through. And hopefully that kind of makes sense. It's like, okay, if this is too large of a thing, it's going to overpower the randomness. Versus also, if I just do something really, really small, well, it's not going to matter too much. Like it's basically on top of each other because this part is just not being increased enough, And then as we get, oops, press the wrong button here. If I increase this down to something smaller, then we actually see something that starts drifting away from here. And you can start seeing as it's positive, small values don't matter as much, and it starts drifting forward. Okay. Any questions on these basic models? White noise, random walk with a drift. Okay, cool for me to move on. Okay, so this is when we get into some more interesting modeling and stuff. So this is actually when we actually do some things like AutoRegressive model and then moving average model, and then we combine them together into one super model, right, into ARMA. And so we'll talk about these two. So our first part, I'll go ahead and run this and make sure it's in here. You'll see that in this equation that looks kind of funky, you can just say, hey, I see the relative parts. I see there's some value being added on every time. I see that we have our YT and then our YT minus 1, so it's correlated with each other, right? And then also adding this random noise in here. So this is our autoregressive. And what's different here is that we have this new symbol phi, right? And this phi is being multiplied by the value from the previous part. So we can adjust phi however we want. So for example, if I put phi equals 0, well, phi equals 0, this should actually not, I wouldn't call it the white noise. I guess it is with a mean, oh, I guess, sorry, it is right here, mean of mu, right? So you would actually start off with this part. This is basically like the random, or not random walk, but basically, it's like a random walk with a drift, because this value would exist right here. So if you set this to 0, basically this part completely goes away. Oh no, I'm sorry, I misspoke. I went ahead of myself. If I set this to 0, this whole part goes away completely, and all I have is mu and epsilon. So basically, it would be, whatever the randomness of epsilon is, which remember the mean is 0, and then plus some value mu. So it's going to stay around mu. It's going to hop around mu every once in a while. If I have mu or phi less than phi, phi, okay. If I have phi less than 0, okay, this will actually have an oscillate. And so hopefully that kind of makes sense, is that we have this basically the part that's likely to, what's it called? It's going to be random on this part, and it's still gonna be related to what was previously, but it'll have less of an effect, okay? And versus something where we increase phi, right? If we increase this, then what we'll have is that those points are actually becoming more important because we're increasing that value. We're kind of like souping it up, right? And this is where we get something that's autocorrelated, which basically just means that it's correlated with itself. It's correlated with its past points, okay? So I think the best thing to do is kind of see what happens here. So I create a little function here, create AR time series. I add my phi, my epsilon, my mu, I just set that, and endpoints 100. Start with something small. I think we started with something small, yeah. And so basically I'm just generating my points right here, right? My date range, and then I get my values. And this right here, I am doing a for loop to kind of make it more explicit, right? I think you might be able to make this more efficient, but this is to also makes it a little easier to read. So basically for E and my epsilon, which I should be passing in, which is going to be a range of epsilon, our random values, okay? I'm basically going to go through it and say, okay, our next value, Y, is our previous Y times phi plus epsilon, right, plus mu. Okay, and I'll basically repeat this over and over and over again, and I give the values without a pen. So I just keep repeating this over and over again, and it's literally just emphasizing, if I had to rearrange this, it would be mu plus this guy right here, plus epsilon. So hopefully you can see that's basically what's going on here. I go ahead and repeat it, and I'll make my time series. So if we check this out now, I'm going to basically start off with an average of 0, standard deviation of 4, 100 points, and I'm going to go ahead and generate my epsilon. And then I made this little fanciness right here. Basically, just have a bunch of phi's. So I'm like, all right, like if one phi is good enough, let's try all the phi's, right? So I started off with like 1.10. I could pick some interesting ones. Okay, I have 0 here. So these are a bunch of positives. Here's some negatives and decreasingly negative. And basically, I'm just going to go ahead and just make all of these time series. Okay, and now I have a cool plot I can show. And you can see here all our different phi's. So note that this all started off with the same epsilon. The only thing I changed was really the phi. So you can see that phi can really change some stuff. So we said like for 0 before, is a 0, we basically have a random, what's called a random walk, right? Or not random walk, white noise, right? So we have our white noise model right here. Basically, it's fluctuating around 0. And in this case, after 100 points, it kind of got a little bit above there, which, you know, it's just randomness. So it's possible it goes there. You can see here on the higher parts right here, we start seeing as phi increases, basically pass points become so more important that all the noise basically completely goes away, or at least it's very, very small compared to the actual increase in each part. But you can start seeing here, hopefully, it's like, oh, that noise is starting going away. We're starting to see this autocorrelation where it depends more and more on the previous value, okay? And you see here for less than 0, right? So these are negative numbers, 0.9, -1, and then -1.1. You start seeing this oscillation in here kind of occur. I think I chose -0.9 because you couldn't really see much happening within, like at least visually, for smaller values, but that value would still have a tendency for oscillation. And you can see those oscillation points. Basically, it's getting trapped in this little bit of randomness until the randomness kicks it off. As the negative part gets bigger and bigger, what happens is that that randomness can't kick it off anymore. Basically, it gets kind of stuck and says, all right, I'm just going to do oscillation now because that's the only thing that matters is the previous point, but it's subtracting off. So if you imagine like your value is 1, and then you're the next time you're basically doing a -1, then you're going to go back down. But then since you're minus, you'd go up, right, the next time, because you're -1, so +1. So you go up and down, up and down, up and down, up and down. And because it increased, since you care about it from the previous time, if you increase this negative point, basically all that matters is whatever the previous point is. So you can see here is that our random noise isn't allowed, basically can't push it off that edge. So hopefully that makes sense. Does that make sense to you guys? Thumbs up if that explanation was kind of clear. Yeah, kind of. All right. So I want to emphasize like why is this doing it? Because like oscillation, like okay, like I could say it oscillates, but you can say Victor, like but why, right? Which you should ask, right? You're like, well, I need to know, right? If I'm going to make these things. Again, you can think of it like when you have the first value. If the first value starts at like let's say it's at 0, and then random noise, or like let's say there's no random noise, or let's start off with 1 with no random noise. And say the next value then is going to be the value times negative, times a -1. It's like, oh, okay, well, that's going to go to -1 now, right? And then the next value is going to take that previous value of -1 times -1. Well, that's going to be 1. And then next time will be -1 and 1 and -1, 1, -1, right? Going back and forth. If we add a little bit of random noise in there, okay, what happens is that sometimes the random noise will be big enough where it won't be like, even though it should be -1, but we add a random noise of like, 3, it's going to be positive. So this is where we actually see, like, even though it's negative, we actually get some like non-oscillation here. But at times when the random noise might be relatively small, which we kind of see right here, right? The random noise is relatively small, we get more of this oscillation. But when that random noise is big enough, right? This is all random noise, then you start seeing it not being oscillating anymore. But as we increase the negativity of phi, basically the random noise, it doesn't matter anymore. It's not big, it's not strong enough, like it's not strong enough to kick it out of this value. Because you can see the values kind of go at most about like maybe 12, at the highest point. And you can see here, well, these are getting up to like 25 and stuff. So this is getting too large for it to compensate for. And so you just get oscillation until the point right here where essentially all you have is oscillation. Okay. Yeah, hopefully that clears things up then, of like why it's oscillating and why this random noise matters on why it's not oscillating as much. Cool. All right, so I'll move on to our moving average model, right? So this is another kind of variation, like you can see here, is our base equation. In this case, you'll see that it doesn't actually have, did I write this right? Oh, I think, No, this is right. Okay. So this is basically, you can see there's very similar, except there's one important part. In this case, it doesn't seem to matter about the previous point. It's actually mattering about the previous noise point, our epsilon, right? So in this case, it's the same thing as phi, but in this case, we actually care about the noise that's being inputted in there, right? And so the same thing, basically, we have, if it's 0, essentially this part cancels out, and you just have the white noise model. If it's less than 0, it will also oscillate, and greater than 0, it will still, it'll correlate with the pass, because this right here is already being incorporated into the previous one. It's just not the direct point. It's more like you are correlating the noise factor. So there's something in there that's basically making it related to the pass, but it's not the actual point itself. Okay, so it's kind of an interesting model. So you can see here, we'll do the same stuff right here, and you can see basically do the same exact thing, except this time, instead of having our y, right, value, we have our epsilon, our previous epsilon value, epsilon I. You see the next one is epsilon I plus 1. And I could have rearranged these indexes. These indexes might be a little confusing, but oh well. All right, so I have this part right here, and I basically make these values. So there's my function. I'll generate my epsilon, right? And then I'm going to create these different thetas, and these are just the ones that I kind of found interesting. Okay, and then we'll go ahead and just to kind of check this out, you can see our different thetas going on here. So our different values of what they look like. Say that, for example, January, you can see that they're still kind of going through some kind of pattern. Hopefully you can kind of see a little bit, but of course, we humans like to see actual visuals, so we can actually go and plot this series out. And now we can actually see these different parts. And this is where it's a little bit harder to tell, because you're not looking off the pass point, you're looking more off of the, what's it called? The noise factor itself. So what you'll kind of see here, like it's kind of hard to see, but I think this spike does a pretty good job, is that, for example, our theta equals 0, this is kind of our baseline right here, right? And you can see here that we have this small spike and then we come back up. But in this case, we actually have a strong, what's it called? A stronger kind of negativity on here. And so we actually can have these fluctuations in this part. This one's a little harder to see, to be quite honest, just because you're not looking at every individual, like you're not looking at the pass point, you're looking at the pass point's noise. And that noise is just harder for us to see because us humans. But we could, if we were to go through autocorrelation functions, we can actually pull this information out and see that, hey, these would actually be autocorrelated on those parts, or if we have oscillation and stuff. So this is where like it's a little more subtle, but it definitely does exist. And you can kind of see, like, I don't know, I'm trying to think if there's ones we can really see it. It's like, not too much. It's tough when the values are kind of small. Okay, but just know that basically it's going using its past, what's it called? Its past noise basically to get the next factor. Okay, any questions? I know that might be the best kind of example because it's a little harder to see. Okay. All right, so our last part is our ARMA model. And our ARMA model basically is just like, hey, we have our moving average model, we have our autoregressive model, let's just stick them together, right? And so essentially that's what happens. We have our two parameters, our phi and our theta, and these are basically representing these parts in here. So obviously if we have, for example, theta equals 0, this would go away and we just have our AR model. And then if we have our phi equals 0, we would just have our MA model. And then sticking together, we have our ARMA model. Okay. And note that there's not a reason why you can stop, like you don't have to stop there. This is when you can start saying, okay, like let's have it pretend, and this is probably, I'm guessing this is the part where you start having some fun, like start messing around a little bit and seeing like what you can do, is you can start defining and say, hey, you know, like let me think of not just the past point, but what if the past 2 points or 2 points ago, and say, what if that's the one that kind of like factors in? And so you can kind of have this like autocorrelation from like, you know, previous points, not just the previous one. It's almost like a weighted average, but instead you're having the previous one be equal to 0 versus like having equal to 1. So yeah. Mm-hmm.
The thing is, I mean, you're not touching on it right now, but did Eric and Ala did you both finish the section?
I'm sorry?
Eric and Ala, no, okay. I didn't know where they were up to in the section.
Mm-hmm. Yeah, they haven't. I don't think people have gone through it yet, right? So welcome to share. Like, if you have something that you want to.
No, it's gonna get off topic, but when you get to Sarima, where you're starting to do, you're going with 3 numbers on ARMA, and then your 3 numbers plus your seasonal for your seasonal order, and then choosing which one it is. And like, you can make for loops, but if you're going to do for loops for multiple things, it's going to take days for you to run through it to find the right one. And I was wondering if you knew of a way to figure out better how to get those numbers. Because I ended up just doing zeros and ones and went by AIC as my metric. Mm-hmm. I tried running a bigger loop for like bigger numbers, but it literally takes forever. Like probably hours for each data point.
Yeah. And I think, so Alan, Eric, what he's talking about is the next model, which I think we'll talk about maybe like our next kind of like study group. I kind of want to just give you guys the basic models at least. But when you can start adding more complexity, like you can see here, like even our ARMA started getting some different parts. So we'd have to consider not just, T-1, but T-, you could get more and more complicated. By its nature, because you're getting more complicated, it's going to run slower. There's ways you can optimize this. To be perfectly honest, is that if you want good speed and good efficiency, usually it's better to either you yourself write it in a faster language, which would be like C, C++. Those are like, like if you want speed, like that's what people go into. Like you go into C code, because that's what Python's really on top of. There are probably the other options, like if you want to drop in the C, you say, hey, has someone else figured this out? Has someone else kind of done a time series with Python and basically not hijacked, but like built on top of C already? So they figured out how to make it optimize within C, and then they do it. One thing you can kind of think about is, if you can optimize this into like NumPy does a pretty good job. So NumPy uses the underlying C code. This is kind of like having a package that already knows what to do in a sense. Is that, is it something more like computer sciencey? But like NumPy basically treats the different stores of like the number stores. I'm trying to not get this too technical, but like where they are in memory, and basically says, well, I know where it is in memory, so I don't have to go look it up. I can just like blindly say, oh, well, I know it starts from 0, and then there's like 10,000 points. Okay, just take those 10,000 points and just shift them up by this much. And it's like, okay, I'm going to multiply by 2. I'm going to shift them up, so they multiply by 2. Versus in Python, when we actually have a list in here, like these for loops and stuff, and especially a list doesn't actually know where they are in memory. It's just saying, oh, I have this number, quick, put it over here. Like it's like someone putting stuff on the shelf or like in their cabinets, just randomly putting things wherever they can. And then they have to like write each part down. It's like, okay, I put my blue cup over in this shelf. I put my red cup over in this shelf, and go on and on, stuff like that. And so when you actually call it like in a for loop or doing any calculation, and it says, okay, it looks up its little paper and says, all right, my cup is in, you can't see me looking at my hand, but like pretending we're looking at sheet of paper, but like, oh, okay, like I need to get my blue cup. Like, okay, blue cup's over here, and I have to pull that up. Where NumPy basically says, all right, I'm going to set up my cups in a nice order part. I'm going to order them from blue to red. I'm just going to put them all like in a line right here. And someone says, all right, go ahead and move the cups down 1 level. And you're like, okay, and just grabs all the cups and they bring it all down 1 level. That's kind of like NumPy is doing. So my suggestion, like I wish I could say like I would be familiar with time series. I don't have personal, like I'm going to be upfront with you guys. I don't have professional experience with time series. This is actually something that, to be quite honest, Aubrey, who joined us last time, Ala was there, actually has a lot of experience, using this in the professional field. She might know, but my guess might be that she could point you to directions, but her expertise is more like in R. So she probably has used other models that are specific to whatever she was using. And this is kind of like where, how do I say this? We can kind of talk about like, how these things work, but getting into like the nitty gritty details of like, well, how do you make it more efficient? How do we kind of speed it up? It kind of relies on the fact that either one, you essentially try to figure out ways to speed it up yourself, which usually means like you get down and dirty and like really try to get into the C code, like Python. And then, or you find another package that already exists that does this really well. And, hope, and one of the things you kind of hope that there's a Python, if you're using Python, use that, or you go into another language and say, all right, I'm going to use this language, or the other kind of fanciness is you drop into that language, perform actions within that language, and then pop back out into Python to do stuff. So that's kind of like my best advice to you. Like, I don't know if, if like obviously this isn't needed for the like project. But you know, obviously if you're getting to the project and you're like, ooh, like how can I make this better? Like you said, like taking a long time for it to process.
Well, it's sort of, if you're making an ARMA model or a SARIMA model, you're going to hit it because you're going to want to figure out what are your numbers that you're plugging in, and what are the best numbers to be plugging in. So currently, I mean, the way it shows us in the notebook, in the labs, is by making a loop. But the moment you're going to get beyond two numbers and you're doing two different sets of combinations, and if you decide to make seasonality one of those, then you're doing a 3 and a 4 number times each of those full amounts of combinations by the amount of zip codes, for example, that you're going to be doing, even if it's only 20. But each zip code is going to take an extremely long period of time because it's running through very possibly over 100,000 loops just for.
Yeah, and this is where I think I know what you're talking about. There was someone, to kind of pull back the curtain, someone from the curriculum team's like, hey, like, have you tried this out yourself to see what they did? They actually made a model to do with all the zip codes. And even with like a relatively basic model, like I ran it on like my like PC, and like it basically took like 2 hours to do the whole thing. And basically it kind of comes down to the fact that like you're doing more complicated parts, and that's reality of just like you're doing this. So one solution you can do, if you want it to work, is instead of, you know, like let's say you optimize it, or there's no way to optimize it, or like I don't have time to optimize it, you can try it on a smaller set. And that would help basically with like its exponential factor. So like obviously if you have more zip codes, you're not going to go up by like, if you increase the zip codes by 10, like 10 times that amount, you're not going to increase your time by 10. You're going to increase your time by some huge factor of 10, like 10 to the power of something, because it's going to increase it further and further depending on what the efficiency are of like that specific, you know, function. This is where, to be honest, like, you know, as a first project kind of deal, or like a project going into here, it's always useful to start it with a smaller data set and say, well, let me go and try like in my opinion, I try to go something like realistic. It's like, okay, let me try it with like a smaller state. Like, let me try it, like, you know, Arkansas or something, all the zip codes in Arkansas, try this model and see how well it runs and see how well that performs, and say, okay, looks pretty good. Let me go and try it with a larger data set, you know, before trying to, you know, this would be like realistic case before you like invest and like spend $100,000, $200,000 to run like this huge model, because maybe you just need more hardware just to crunch all the numbers. The worst thing you can have is like you spend all this money to do it, and it turns out, oh, that wasn't a very good model. Oops, like I just spent a lot of money to this. My background's computational physics. I had stories of this happening to a lot of physicists where they would have simulations where essentially they would have these simulations run for like a month, 2 months, 3 months, and you'd come back and you're like, oh, overflow error. And they're like, shoot, like I did not think about that beforehand. And now all that time, computing time I could have had is now completely down the drain, which computing time equals money essentially. So that's kind of like, that's the best I can really answer this. Like, I wish I had like more knowledge to say, oh, you should just use this thing, and that would be the right solution. Maybe I'll do a little research and see what I can find for you, and maybe I'll Slack you too, specifically. And of course, you know, ask Raphael, ask an instructor. Honestly, maybe even Slack Aubrey, because I think Aubrey would have professional experience.
Yeah. Maybe I'll shoot something over to Aubrey. Yeah, no, Raphael also doesn't have industry experience, so it's like, Raphael's very helpful. Like, love him. He's great. Yeah. But like specifically in this, like with you, when you don't use something in industry, you know it only to a certain extent, and that's just the way it is.
Yeah, it's just like with the theoretical knowledge, like, oh, we understand how this works, but applying it with some specific type, really, it's like, oh, what do people use in the industry? Yeah.
Yeah, I will say one thing. When you're talking about amounts of zip codes for the project itself, Raphael told us choose a region, and like, you know, 20 to 40 zip codes, whatever it was, depending on where you were choosing. Choose an area, and then look into that. none of us ran models on the entire data set. That would be insane.
That's a smart thing to do. I remember talking to someone, I can't remember who it was, and they were talking about like using this whole zip code. I'm like, ooh, like I am not going to recommend that because that's, you know, it might work for simple models, but once you get a large enough model, like even a relatively simple model, you're going to be like, oh shoot, like it's not going to be good. So maybe one thing you could do, like at least for that, just to play around with it. Like I'm assuming this isn't like a huge part of your project. One thing you could do is kind of slice it up and say, all right, let me try it with like a baby set. Like, let me try just like 1,000 zip codes. Like, it's like, okay, this is really small, but let me just try to see if it works, if it's my code or if it's like the number of values I actually have.
Small is like 2 zip codes.
And so that, yeah. So in that case, I think you need something more powerful. I think either it's something direct in the code where it's like really inefficient, like if there's for loops within for loops, or there might be like, you know, maybe just depending on how it's implemented, maybe there's better tools that have figured it out already. Yeah, cool. All right. I know it's off topic, but hopefully all of you found that was useful too. So your future, you know, kind of waits in that way.
Not that far down the road, so.
Cool. Well, no, I really appreciate you coming in and joining us because it's nice to see, you know, especially you already into the project, if not close to being done, if not done already. At least one.
Finished.
Congrats.
I saw you were doing a thing. I'm like, you know something? To be honest, this helped me a lot. It was like, because the project, I wasn't dealing with this stuff in the project. Mm-hmm. Because like I said, once you're starting to use a ARMA or a SARIMA model, your detrending is getting done. Anything you're doing with this stuff is more to figure out what you can find out about the information. It's not, so it's more like your EDA, but even then you don't necessarily need it. So I think I got a better grasp on this stuff now than I had before, which is very helpful.
Oh, good. Awesome. Cool. You know what? I realized I knew we were a little bit over. We're actually not that bad. I thought it was a lot worse. So I'll actually stop the recording here unless you guys have any other questions about anything we kind of talked about. All been really good.